Hello students, today we're gonna solve a problem on normal and tangential components. And like always, from the picture, you can see that in this problem we're gonna include a motorbike in our problem. So let's see what's our problem. The learning objective of today is that solve a curvilinear motion problem. And in the problem, we're going to look for normal and tangential components of velocity and acceleration. So in the particular example we're going to solve, we'll apply the normal and tangential coordinate system, that the theory that we have learned in previous video, and we'll determine the direction and magnitude of velocity and acceleration. And here's the bike for us that we're gonna include in our problem. So let's see what the problem says. When the motorcycle is at 10 meter in y direction, so if we see the diagram that we have here, this is the path of the bike. So the motorcycle follows this path. It says when the motorcycle is at 10 meter, the velocity is 3 meter per second, and it's increasing at 2 meter per second square. And the path is defined. So the path of the motorcycle is y equals to x cubed over 27. It's asked us to determine the direction of velocity and acceleration. And also the magnitude of the acceleration. So let's see what things are given. So here's our bike that came in, and it starts that path, and now it's at the position where it says y equals to 10 meter. Now what are the things are given? It's given that the velocity is 3 meter per second. And it's increasing at 2 meter per second square. So now it's meter per second square, so we know it's an acceleration. So, and we know for here, for normal and tangential component, we can have a AT, which is tangential component, and AN, which is normal component. But we know velocity is a tangent to the path of motion. So the velocity increment at this point will be the tangential component. I see there's a typo. I think we have used 5 here. Yeah. So let's solve the problem. So what are the unknowns? We want the direction of the velocity. So this is defined by the direction upward. So we're looking for the direction of the velocity and the direction of acceleration, and also the magnitude of the acceleration. So these are the things unknowns. So we have identified then our knowns and our unknowns, and we have our diagram ready. So let's go for the solution. So first, let's figure out what is our coordinate. When y equals to 10 meter, if we plug y equals to 10 in the equation, path equation that is given, we will get x equals to 6.46 meter. So now let's work on the first thing, that is the direction of velocity. If we take a derivative of the path y equals to x cubed over 27, if we take derivative of that, we get x squared over 9. Now we know the current position of the bike is 6.46 meter. So if we plug that value in the first derivative, which is dy over dx, and we know that is the slope, so we just plug the value 6.46 into the derivative equation. We get y derivative equals to 4.64, and which is a slope. So we can take tan inverse of that, because tan theta equals to dy over dx. That's the slope. So if we take tan inverse, it gives us 77.84 degree. This angle is with the x direction. So we're going to talk about that. So we have find out that the direction of the velocity is 77.84 degree. So now let's move on the acceleration part. For acceleration, what we're going to do is that we know the equation for acceleration for tangential and normal component at with a unit vector ut and plus an, the normal component multiplied by the unit vector in normal direction. So we know that at, the tangential component of acceleration, is given. So first part is fine. The second part, v squared, we know v is also given. Only thing we don't know is rho. So rho is the radius of curvature, and then we know there is a given equation for radius of curvature. You can see the derivation of this in any math book. But yeah, for now, just know that the equation to find the radius of curvature is 1 plus dy over dx whole square whole to the power 3 by 2 divided by the magnitude only, so positives, it's a positive bar of second derivative of y. So if we simplify it, 1 plus y prime whole squared, so first derivative whole square over to the power 3 by 2, and the lower part, and the denominator we have the second derivative of y. So we know that we have found the value of y prime in previous slide. So only the thing we don't know is the y double prime. So if we take the second derivative of the given path, we found y double prime is 2x over 9, and if we plug the value x equals to 6.46 meter, we get the value. And if we plug all the value in the equation of radius of curvature, we found that the radius of curvature is 74.34 meter. So now we know all the item we need for acceleration. So if we plug those value, at, which is given 5 meter per second square, and the normal component velocity is given 3 meter per second, and if we plug the value of rho, 74.34, so this is our acceleration. So if we simplify, we found a equals to 5 ut in tangential component and 0.121 in normal component. To find the magnitude, we know the equation. A equals to the first part, tangential component whole square plus the uan normal component whole square, and the square root all over it. So we see that it's if we take that, we'll get the value of 5.001, which is almost 5, because the an component is very small. So the magnitude of the acceleration at that point when y equals to 10 is 5 meter per second square. So we found the magnitude. We're still looking for the angle of acceleration. So we know if we want to find the angle, we can always take tan inverse of the normal component over tangential component. If we do that, we get the angle 1.4 degree. So now for velocity, it was easy because velocity is the tangent of the motion path, but acceleration is a second derivative of the path, or first derivative of velocity. So this angle 1.4 is kind of complex to see where it is. So we'll draw a diagram. So if this is the blue line is our x-axis, and the tangent for the velocity, we found the theta, which we found in previous slide. So now the acceleration is derivative of velocity, so it will be the angle will be on top of the direction of velocity. So we put an normal component as y, and we put at as a dx. So the angle we get it will be the phi, which is with tangential component. So the total angle of acceleration with the horizontal axis would be the summation of both theta and phi, so which is be 79.24 degree. So one thing, if so my acceleration, so the bike is moving upward, so that's why my angle is this one, and this one was my velocity angle. If my bike was moving downward, then the angle what we would have got for the velocity would have been this theta, but my acceleration would be in this direction. If my acceleration was downward, in that case we can take tan inverse of AT, tangential component, over normal component. So if we take my tangential component, which is in t direction, right? So in y as our y component, so this will be this part, and a normal component in dx in denominator. So the angle we will get from there, so this will be our dy because we put it in the denominator at the top, and then our dn would be here, so the an is here, so the angle we will get is this angle. We can call it phi prime if this is the scenario if my acceleration was downward. So in this case my angle would be this, and to find the angle with horizontal we have to sum theta plus this angle, which is 90 degree, plus the phi one. So if my motion was downward, and if I take this AT over AN instead of AN over AT, my angle would be theta plus 90 degree plus phi 1, so theta plus 90 degree plus phi 1, which would be this one, and minus 180 to find the angle. So so we can take also negative 180 to find the exact angle between the horizontal axis and the acceleration if it was downward. If still you need more clarification, you can post a question and I can clarify more. But I guess that's clarified. That's the answer for our angle. So the answer would be magnitude of the acceleration 5 meter per second square, and the angle that the motorcycle makes with horizontal axis is 79.24 degree upward direction. So that's it. Thank you so much. In the next video we're going to solve another normal and tangential component example that will include a train. But till then, thank you.